Hello friends, in today's question, a ring of mass m and radius r is rotating with the angular speed omega about a fixed vertical axis passing through its center O, with 2 point masses each of mass m by 8 at rest at O. These masses can move radially outwards along two massless rods fixed on the ring as shown in the figure. At some instant, the angular speed of the system is 8 omega by 9 and one of the masses is at a distance of 3r by 5 from O. At this instant, the distance of other mass from the O is. So it is given that this is a ring which is rotating about its axis with the angular velocity omega, and we have point masses at point O, and each point mass is having a mass of m by 8, and they are free to rotate about these rods, and these rods are also massless. And at some instant it is given that one of the mass is at a distance of 3r by 5 from point O, and we are supposed to find out what will be the distance of the second mass, so that the angular velocity of that particular system is coming as 8 omega by 9. So in this case, we are going to solve it by using the conservation of angular momentum. And let us redraw the figure as initial condition and final condition. So initially it is given that this is a ring and it is rotating about its axis, which is passing through the center O, and there are two masses, and this is the one massless rod and this is another massless rod. And initially the masses, let us suppose, is given as m1 and m2, and both the masses are at the center, and at that particular moment the angular velocity is given as omega. In the second case, we have the same circular ring and it is rotating about the axis which is passing through the center, and in this case now the angular speed of the system is given as 8 omega by 9, and in this condition these are the two massless rods, and now it is given that one of the mass is at a distance of 3r by 5 from O. So let us suppose this is the mass m1 which is at a distance of 3r by 5, and we are supposed to find out what will be the distance of other mass from O. So let us suppose this is mass m2 and it is at a distance of x from this center O. So you can say this is our initial condition, and this will be our final condition. So we are going to find out initial angular momentum and final angular momentum, and using the conservation of angular momentum equate them and find out what will be the value of x. Okay. So let us solve it. So we say initial angular momentum. Initial angular momentum, let us call it as L initial. So the initial angular momentum will be, first of all, because of the rotating ring. Okay, so you can say initial angular momentum is due to rotating ring and two masses at the center, 2 point masses rather at the center. Now it is given that the 2 point masses are lying exactly on the axis of rotation. So therefore we can say that since the point masses lies on the axis of rotation, therefore their moment of inertia will be equal to 0. Now we already know the formula for the moment of inertia of the ring around the axis which is passing through the center. So we can say moment of inertia of the ring about the axis passing through its center will be equal to mr square. Therefore, the total initial angular momentum which is written as L initial will be equal to moment of inertia of the ring and multiply with the angular velocity, and we have this as mr square multiplied by omega. So this is our initial angular momentum, and now we are going to find out final angular momentum. Final angular momentum, let us suppose that is given as L final. So once again we can say that in the final angular momentum the position of the point masses have changed. So as the position of the point masses have changed, it means they have moved from their center of the axis to new position. The moment of inertia of the system is also going to change. So we can say point masses, let us suppose we call them M1 and M2, moves to new position with respect to axis of rotation. Therefore, we can say that moment of inertia of the system will change. Now the system consists of the moment of inertia because of the point mass and the moment of inertia because of the ring. The moment of inertia of the ring will remain same. So you can say from here that the moment of inertia of ring, let us call that as I ring, will be equal to mr square. And we can find out moment of inertia of the point masses. Moment of inertia of the point mass so point mass m1 is at the distance is equal to 3r by 5 from the axis of rotation. Axis of rotation. Therefore, we can write its moment of inertia. Moment of inertia of m1, let us call this as I m1, will be equal to, its mass is given as m by 8 and the distance from the axis of rotation is 3r by 5. So this becomes 3r by 5 and whole square. And for the point mass m2, point mass m2 is at a distance of x from the axis of rotation. Therefore, we can say that moment of inertia of m2, let us suppose it is given as I m2, will be equal to m by 8 and x square. So we found out the moment of inertia because of both point masses, and now we can simply solve it. Therefore, we can say that total final moment of inertia, which is given as L final, it will be equal to, total moment of inertia is given as I final. So we can say I final will be equal to moment of inertia because of the ring plus moment of inertia because of the point mass m1 plus moment of inertia because of point mass m2. So we get here I final is equal to, ring is our mr square plus this moment of inertia because of m1 is m by 8 and we have 3r upon 5 whole square plus this is m by 8 and x square. Therefore, final angular momentum. Therefore, final angular momentum, which is given as L final, this will be equal to, L final will be equal to moment of inertia final and multiply by the angular velocity, speed, and angular speed is given as 8 omega by 9. So this becomes as 8 omega by 9. Therefore, we can say that our L final is equal to mr square plus m by 8 3r by 5 whole square plus m by 8 x square and multiply by 8 omega by 9. Now we are going to use conservation of angular momentum. So you can say conservation of angular momentum, initial angular momentum, that is L initial will be equal to L final, and initial angular momentum is our mr square omega, and final angular momentum is our mr square plus m by 8 3r upon 5 whole square plus m by 8 x square and multiply by 8 omega by 9. So here we can cancel m throughout, and also omega cancels out, so we are left with, and multiply this on the left side, we get 9 r square by 8 is equal to r square plus, this will be coming as, this will be our 9r square, and this will be our 8 into 25 plus x square by 8. Okay, we can further solve it, making left and right adjustment. We can say that our x square by 8 will be equal to r square as common. We get 9 by 8 minus 1 minus 9 by, this will be coming as 200. So further simplification, this gives us x square by 8 will be equal to r square multiply by, this will be 2 by 25, and this further gives us that x square is equal to 16 by 25 multiplied by r square. So therefore we can say that our x is equal to 4 by 5 times r. So this is the distance of other mass from O. This is the distance of mass M2 from point O. And we check the option available to us. We can say the option number D is the correct option. So therefore we can say that option D is correct. So this completes the question. Thank you.